The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone, and welcome to the IIVS-sponsored webinar on practical experiences with the in vitro 3T3 phototoxicity assay. This webinar is provided as part of IIVS's educational webinar series and is funded through contributions to the Institute. Today's webinar will serve as a follow-on to our previous webinar that discussed the 3T3 phototoxicity assay. Some of the topics that we cover today will be the selection of solvents and reagents used during the assay, challenges with neutral red itself, and solubility issues with test articles. Before we start, I would like to take a moment to make sure that everyone is familiar with the webinar control panel. All participant audio has been muted and will remain so for the duration of the webinar. You may ask questions by using the question feature at the bottom of the control panel to the right. Click on the arrow to minimize the control panel and view the questions window. Questions can be submitted anytime during the webinar. They will be answered during the last 10 minutes. We're recording this webinar and the question and answer session at the end. Any questions that are not able to be answered within the scheduled webinar time will receive a written response that will be distributed to all webinar participants along with a PDF of the presented slides and a link to view the webinar recording within 2 weeks. Let's meet our speaker. Today's presenter is Allison Hilborough. Allison has been working with and providing training on in vitro test systems for 10 years. Allison is currently serving as the IIVS Study Director for the
as I think many of you probably already have familiarity with the assay through your own experiences or through the OECD test guideline literature. The specific topics I've chosen are those commonly asked in my tenure as a study director, in my discussions with other users, and also frequently asked by those who are interested in starting up the assays within their laboratory. We're going to start off with an overview of the assay, and then talk about some of the assay checks and controls that we have in place, why those are important, how we monitor different reagents, results, and responses. The 3T3 assay is well established, and we've been performing it here at IIVS for about 20 years. But we found in our experiences on occasion, we do have challenges, and we need to stop what we're doing and think about what's happening and take a closer look at the assay responses. So today we're going to focus on some of those specific experiences, such as neutral red, solvents, and solubility, and then we're going to wrap it up with a case study on solubility. At IIVS, we perform the 3T3 phototoxicity assay as outlined in the OECD test guideline with some modifications. In general, we're going to start with a solubility pre-assessment and then move into the assay steps, starting with cell seeding for 24 hours. After 24 hours, we're going to prepare our dosing dilution series, add that to our 96-well plates for 1 hour, incubate cells, and then expose one of the plates to the UVA exposure, and one plate will be exposed to the dark exposure. After the 50-minute exposure and UVA are dark, we're then going to terminate our treatment and put the cells back to the incubator for a 24-hour post-expression period, where then we'll add our NutriRed for 3 hours. After the 3-hour incubation with NutriRed, we'll then move into our plate reading, solvent addition, and finally our phototoxicity assessment. So today we're going to really focus on the pre-testing solubility assessment as well as the assay step involving dilution of the test article and the NutriRed. As I mentioned earlier, there's a number of assay controls and checks in place that should be continually monitored and evaluated. The first being the positive control. Chlorpromazine is our positive control, and we'll prepare a dilution series and run it with each assay. We also have negative or solvent controls, which are treated on each plate, and we use those to determine our relative viability of our UVA or dark exposure. And then there are also a number of checks outlined in the OECD test guideline and also in VTOX's protocol number 78, which is essentially like an SOP for the test guideline, which provides a little bit more specific guidance and information on the procedures. And there's a number of other criteria identified in that using the optical density. So the solvent control comparison between the light and the dark plates should be greater than 80%, and we use that to make sure that the light itself isn't causing excessive toxicity. In addition, the documents also describe acceptance criteria for mean optical density signals. The signals at the end of our assay should be robust yet sensitive enough to be able to capture a range of responses. The OECD test guideline outlines an acceptance criteria of 0.4 or greater, and in VTOX 0.3 or greater for the optical density signal. The results of the controls and acceptance criteria should be continually monitored through a database. And it's crucial that each laboratory conducting the assay creates their own internal database to evaluate their assay responses over time. They will be important to evaluate assay acceptability and your performance. Ideally, before your assay begins, you're going to assess the solubility of each test article. And then finally, since we can't see what's happening in our 96-well plates, we should be performing microscopic observations at defined steps throughout the assay. So let's go ahead now and dive into one of the assay challenges, one of which you may have seen before in your experiences. Maybe you weren't sure what you were seeing, and that's NutriRed crystallization. In 1998, a publication came out describing how NutriRed crystallization occurs due to pH instability. The laboratory that had discovered this started using a different medium, and when they started using this different medium, they noticed that there were fiber-like structures forming within their medium. And the medium they were using was prepared with NutriRed. So they determined that the NutriRed was actually precipitating out as a toluene red when the pH was above 7.6 in their salt solutions. And they also determined that you could eliminate this crystallization event by using the appropriate buffers like HEPAs or sodium bicarbonate in the medium. And again, the buffers are used to maintain the pH under certain conditions. So the question would be, why should we be concerned about NutriRed crystallization? Well, first let's take a step back and think about how NutriRed is used in our assay. So here is a graphic of a cell. NutriRed is an uncharged dye and passes through the cell easily. When NutriRed moves into the cell, it accumulates in the lysosomes, which have a pH of 5.5 because it actually gets a charge on it. So we can then use that information, and with the trapped NutriRed, when we lyse our cells, we can measure that on a plate reader. So if we have a crystallization event, the first concern would be, will that be able to get into our cells? And the second concern would be if we have crystallization in excess, if it attaches to our cell membranes or it remains adhered to our plate, we could inflate our final optical density signal. At one point, we started to see minimal amounts of NutriRed crystallization during our routine assay conduct, and we hadn't really had any major changes in our assay procedures or supplies that would really have stood out as a cause for this. So with that, we started doing some R&D experiments to see if we could induce crystallization and see if there were any impacts of serum, temperature, and CO2 on that crystallization. And you'll see the graphics to your right there, a couple images of NutriRed crystallization that we had seen. And with the design, we took our standard medium and we looked at those different conditions. So one medium had serum, one didn't. We incubated at either room temperature or 37 degrees. We also had it incubated at 5% CO2 or atmospheric CO2. We checked for crystallization after 3 hours and then again 24 hours later, and we also monitored the pH over time. Now what we found through this R&D experiment is that we actually were able to induce crystallization. The medium containing serum and incubated outside of the 5% CO2 had the greatest amount of crystallization, and we also noticed that this medium also had the greatest shift in pH when the medium was incubated outside of the 5% CO2 incubator. So the key takeaway points here are that when you are running the assay, you want to make sure that the medium that you're using is supplemented with the appropriate buffers and incubated under the appropriate conditions. You should also limit the amount of time that the plates are outside the incubator, especially if you're working with a large number of plates. You could prepare smaller batches of Nutri-Red also to make sure that you're not having an excessive amount of time that the Nutri-Red is sitting at room temperature, being ready to be added to the plates. We also would break the number of plates. If we have a large group of plates, we would break it into smaller groups to minimize the amount of time they remain at room temperature. And also, especially important, is that we check our plates prior to the Nutri-Red addition and again during our incubation for crystallization. Now, one of the reasons that we want to check before we actually add the Nutri-Red is that if we see levels of cytotoxicity, we want to make sure that our signal at the end of the assay matches that. In addition to occasional crystallization events, we also started to notice declines in optical density signals when we received a new lot of Nutri-Red. We initially noticed the problem too when we had seen precipitation in that particular lot of Nutri-Red stock. So what we wanted to do was see if we could prepare our own stock here and then compare that signal to the previous signal that we got. So we took a confluent layer of 3T3 cells that would be about the same amount of confluency at the end of the assay, and we added 33 microgram per mil dilution of Nutri-Red in assay medium to those cells, and here we have our optical density signals. This would be the old stock that we had used, and then this is the prepared stock. And as you can see between the two batches, the stock that we had been recently received had optical density signals of about 0.3, so that would have not passed the OD criteria as outlined in the test guideline, and it barely met the criteria as outlined in Vitox Protocol 78. Whereas the prepared stock that we started making here at IVS actually met that acceptance. Shortly thereafter, we also started noticing some changes in our filters that we've been using to prepare the 33 microgram per mil Nutri-Red. And we had typically been using a bottle filter, and within that bottle filter, the procedure and process of the amount of time that had taken for the filtration to occur had increased from lot to lot. So what we did is we checked the vendor, and what we found was that actually there were changes in their manufacturing processes, which we thought perhaps contributed to the difference in the responses. So moving forward, we now use syringe filters, and again, optical density values here, looking at a syringe filter with a stock, a syringe with an aliquoted, and then a bottle filter. And you can see, again, that between the syringe filter and the bottle filter, there is quite a bit of difference in our optical density signal. We also started to see high sensitivity in our assay, where our positive control was falling outside of our acceptance range, and we were getting high mean photo effect, or MPE values. At the time, we had prepared a new batch of chlorpromazine using a different lot of the same catalog DMSO. And upon further investigation, we contacted the vendor, who recommended that we use a different catalog of DMSO. So we decided that it would be worth investigating the different lots of DMSO versus the catalog number recommended by the vendor. So we have chlorpromazine, 3 different batches, prepared in the DMSO that had a high failure rate. This was one specific catalog, but 2 different lots. So lot 2 was a new DMSO lot number of the same catalog as lot 1. And then we had our 3rd chlorpromazine batch, which was in the completely different catalog recommended by the vendor. Now, if you look down at the mean photo effect, the percent solvent control comparisons, and the optical density values, lot 1, as well as catalog 2 DMSO, performed quite poorly. And those results would not have met our acceptance criteria. The only one that worked well was lot 2. And below here, we have graphic representations of the data obtained by the Phototox 2.0 software, where we have our viability on our y-axis and our concentration of chlorpromazine on our x-axis. And you can see, visually looking at them, they look fairly close in terms of the response curves, batch 1 having a little bit more variability than the other 2. But again, even closer looking at the MPE solvent controls, we did not meet acceptance criteria for the 2. In my experiences with this assay, one of the biggest topics of discussion has been solubility. The OECD test guideline mentions solubility and dealing with test articles which are not soluble in a number of different places. I highlighted a couple of those places on this graphic here. And Section 18 mentions precipitation should be avoided. 26 mentions cytotoxicity. If you don't observe it at a saturation point, then the highest maximum concentration should be tested. And then finally, Section 56 goes into a discussion of solubility and limitations for the assay. So if you're picking up the OECD test guideline, how do you interpret this? You know, what does it mean when it says should be avoided? Should we remove data points where precipitation was observed? What is the maximum concentration referred to when they discuss it in the saturation point? Is it 1,000 micrograms per mil as mentioned in the test guideline, or is it the solubility based on that saturation point? And then if the solubility is very low, is there a minimum concentration that we would need to have achieved to accurately assess phototoxicity potential? Now that I've covered the OECD test guideline discussions in dealing with solubility, I'd like to share some of our standard approaches. And this was initially presented in our 2013 webinar. In general, when we deal with solubility, the first step that we're going to do is determine the most appropriate solvent with our test article. And also we might look into what additional measures might be needed, for example, heating and sonication. Our standard solvents include HBSS, DMSO, ethanol, and acetone, with DMSO, ethanol, and acetone being the intermediate solvents. And in general, if we find a test article to be soluble in one of those intermediate solvents, we'll then assess how the test article behaves when we return back to the aqueous HBSS. And in general, if we can create a solution in the intermediate solvent, then we proceed with that solvent. If we prepare the dilution series in the intermediate solvent that can't completely be solubilized, we always have to worry about sampling error due to precipitation. But again, we'll try to avoid that when possible through heating and sonication and the appropriate selection of solvent. The most important consideration, though, that we have to consider when talking about solubility is bioavailability. We need to make sure that our test chemical is available to the cells. And so this graphic here, which I like to call the solution to the suspension, really kind of outlines how we handle this here at IAVS. And the first question we have is, how do we assess the insolubility? Can we work with something that's not completely soluble? Is it homogeneous suspension? In some cases, we may find that it's so insoluble, perhaps it's forming a biphasic suspension, or the precipitates are very large. We may need to directly go into addressing other testing platforms. But in some cases, we can also look at running a preliminary dose range finding assay and evaluate results. Is there bioavailability? If we have an absence of cytotoxicity, is it truly non-cytotoxic, or is it because it wasn't bioavailable? If it has a lot of variability in responses and there's no cytotoxicity, we may determine that it's not compatible and, again, end up at our needing to look at other testing platforms. But in other cases, if we do see evidence of bioavailability through some levels of cytotoxicity, we can proceed then with the definitive assays. So what if the above-mentioned solvents, DMSO, ethanol, acetone, don't fully solubilize a test article? Or what if your sponsor is requesting a new solvent? Maybe they have an ingredient that's going to be part of a formulation that they want to test with some solvent that they're also using in the formulation. We have an approach here that we like to follow whenever we're evaluating new solvents. So the first thing we're going to do is conduct a 3T3 assay using that solvent of interest and treat it as a test article. And we'll find in most cases that we're going to be exceeding the limit outlined in the OECD test guideline, which would allow us to assess all cytotoxic responses. And what we want to do is evaluate those responses and assess the MPE, or mean photo effect. And here is a graphic from the Phototox software where we look at the viability and the concentration of our particular solvent. We also want to take a closer look at how that solvent behaves in the concentration that would be used in the assay. So in this example, the 1% is right in the middle, which is what the cells would be exposed to in the assay as recommended in OECD. And I just have a couple of the other points flanking on either side, but you can see that the viability still remains around 100%, and there really isn't a big difference between the viability of the cells exposed in the presence or the absence of light. So once it passes that criteria, we know that it's not phototoxic, we know that it's not cytotoxic at the level we would be using it. The next step would be to take that solvent of interest and test the sensitivity of it. We want to prepare our positive control, which is chlorpromazine, in that solvent and compare that to our positive control prepared in our standard assay procedures, which is prepared in DMSO. And here is our new solvent, and here is our standard DMSO. So you can see the chlorpromazine in the new solvent, as well as the chlorpromazine in the DMSO, looks fairly similar in the dose responses. The MPE values are fairly close, as well as the PIS values. So based on this information, we would be comfortable moving forward with this solvent in our assays. Now I want to take a look at a hypothetical case study where we have a test article that is not completely soluble. We learned this in our solubility assessment that we have a suspension at 1,000 micrograms per mil, and we decided to test to see what concentration we could get complete solubility, which was about 100 micrograms per mil. Now we could take two different approaches here. The first, we could move forward, as we typically do here at IVS, with testing at the OECD recommended 1,000 micrograms per mil, or we could also look at another approach and testing only soluble concentrations. So if we tested 1,000 micrograms per mil as our highest, we'll go down to 16.3 micrograms per mil. And if we tested 100, we'll move down to about 1.63 micrograms per mil. And from the assay, we would have observed precipitation in the 4 highest doses, again, with the solubility about 100 micrograms per mil. With our Phototox software, we do have the option where we can include all of our data points, or we can also edit it to exclude specific data points. So the questions are, what if we analyze only soluble doses, and what if we tested only soluble concentrations? How would our data look, and what would our responses be? And you can see between the two approaches, so approach 1, if we tested to our highest 1,000 micrograms per mil. And approach 2, if we tested only soluble concentrations of 100 micrograms per mil, you can see between the two there's quite a difference in the dose response curve. Most of what's happening is happening greater than 100 micrograms per mil. So if we only test to 100, we're going to miss all of this. Now, what do our final results tell us? Well, this summary table here highlights all the responses when we test up to 1,000 and also has inclusion or exclusion of doses as well as the responses when we test only at 100. So we have our highest doses, our approach in terms of do we edit the data or not, which concentrations would be included, what our MPE value would be, what our PIF value, and what our prediction would be based on that. And below here, I have the OECD test guideline prediction for phototoxicity potential based on the MPE and PIF values. So you can see if we test at 1,000, include all of our doses, we get an MPE of 0.191 and a PIF of 9.02. Our prediction would be phototoxic. But as we start to remove doses, we move from a phototoxic prediction to a probable to a non-phototoxic prediction. And if we only looked at 100 micrograms per mil and less, which is our concentration where we have complete solubility, we're going to predict this to be non-phototoxic. So this could be a bit of a concern. I'd like to wrap up the webinar today with a couple additional consideration and comments on solubility. A number of test articles which were insoluble were deliberately selected for phase 2 of the 3T3 phototoxicity validation study to better understand the assay limitations in regards to solubility. The ranges of solubility were very high to very low, but the assay was able to correctly predict phototoxic potential regardless of aqueous solubility. So what message do we take home from the case study and the results that are presented from this phase 2? There are different opinions and perspectives on solubility, how to handle it, and I think all have very valid points. From the case study, we have shown that if we assess data only using soluble doses, the phototoxic prediction can be impacted. And in working with test articles which are not completely soluble, they should be handled on a case-by-case basis. When we have precipitation observed, we really need to closely evaluate the results. Are they reproducible? Could the precipitation in the doses be a source of variability? Do we have evidence of bioavailability? And in some cases, we may find that we need to consider alternate testing platforms and that the 3T3 assay would not be able to be used for the assessment of phototoxic potential. If we work with materials that are not completely soluble, we also need to understand that the IC50 values may be impacted, especially if there's sampling errors during the preparation of the dilution series. Now, we can minimize those errors using intermediate solvents when applicable. And while we may not achieve precise IC50 values in dealing with test materials that are not completely soluble, both the case study and phase 2 results demonstrate that this assay is able to identify test materials which respond differently in the presence as compared to the absence of light. We should keep in mind that the 3T3 phototoxicity assay is designed as a hazard assessment tool that can tell us if a test material has phototoxic potential or not. I'd like to thank you for your time and attention today. And at this time, I'd like to open the discussion up for questions and comments from all of you.
All right. Thank you, Allison. So at this time, you can go ahead and, if you haven't already, type up your questions in the questions pane. We have a number that we can start with. So the first question, where can I get information on the media to use for the assay?
The SOP provided by the in vitro protocol number 78 is probably the best start for this. It does have a lot more detailed information, and it also includes CAS numbers and catalog numbers for some of the media and reagents used for the 3T3 assay.
Okay, if I see neutral red crystallization, should I repeat my assay?
I think in terms of neutral red crystallization, the important thing first is to make note of what you see and then evaluate your responses. It will probably be on a case-by-case basis. In some cases, we may see very minimal amounts of crystallization, which wouldn't appear to have affected the assay. I've also seen in some cases where a complete plate appeared almost covered with crystals and the signals were quite high. So I think, again, really case-by-case basis.
Okay, how about which solvent would you recommend to use for a cosmetic product like a cream? Or is this not the appropriate platform for these formulations?
The 3T3 assay is really designed to address ingredients for cosmetics, for example, botanical extracts, antibiotics. So solubility becomes a big concern when you start talking about final formulations. The best platform to address final formulations like creams and cosmetic products would be the reconstructed human epidermis.
Okay, how about, could you tell us a little bit about the software that we're using for the data analysis and where you can get it?
The software that we're using is the Phototox 2.0 software provided by ZBET. You can find more information on this, I believe, in the OECD test guideline website. We'll provide a link to that when we send out the written Q&A form.
Okay. So what is the cell concentration that should be used for seeding per well?
We seed our cells at 1 × 10⁵ cells per mil, and we add 100 microliters to each of our wells.
Okay. There's a question about how acetone can be used as a solvent. The questioner was wondering if it interferes with cell viability itself.
The first example that I provided of the assessment of a new solvent in step 2 was actually acetone. We can use acetone, and again, we evaluated to make sure that it didn't cause cytotoxicity itself. In the assay, we're using our solvent concentration at 1%, and we didn't notice any adverse impact of that. As I mentioned in the beginning of the webinar, it's important to create a database. That's where you could start, if you did use acetone, start collecting data and looking at your optical density signals and your comparisons to see how the acetone performs with the assay.
So for the OECD, is it acceptable to have a negative control that shows consistently an OD at the lower side of the scale?
The OECD test guideline does mention 0.4 or greater for the optical density signal. Now, this is also something that has been frequently discussed, or one of the questions that people ask a lot of the time because they have trouble achieving that 0.4. We tend to use the in-detox protocol of 0.3, and again, depending on the assay results, case-by-case basis, the 0.3 may be acceptable.
Okay, so the OECD protocol states that cells with less than 100 original passages should be used for testing. Is there a good source to acquire the cells with a low passage number?
The reason that we use the cells at passages less than 100 because the cells, the sensitivity to light can increase when we exceed 100. To our understanding, there really isn't a good source other than ATCC, but the cells that we typically receive from them are around passage 70, so they typically last about 2 to 3 months of routine passaging.
Okay, what is the range that we normally get on our controls with plus or minus UV?
I think sometimes that depends a little bit on the solvent. In general, though, we typically see values of about 0.3 to 0.5.
Great. How about this one? What if the test does not meet the OD criterion for greater than 0.4 for the untreated controls?
I think, again, this could fall on a case-by-case basis. In some cases, you may find that if it doesn't meet the 0.4, there are other things happening in the assay which would make you want to repeat that particular assay. The Detox Protocol 78 does outline an OD value of greater than 0.3 as a criterion, and we can also use that to evaluate our final responses as well.
Okay, and I think we'll take one more question. There's a comment that one lab is performing the assay under controlled oxygen and temperature conditions in a barrier isolator, and so that they don't have to worry about room air conditions to create problems. Is there any other factor that you can think of that they might want to consider?
Interesting. I think one of the main things that does pop up is that when we run the assay, especially during the exposure to UVA or dark, we do keep our plates at room temperature, and we do use HBSS as our buffered solution for that. Some people have, noted some challenges because of being outside the incubator for so long. So in our experiences, we had started out with EBSS, Earl's Balanced Salt Solution, and found that HBSS was a better buffer for the cell system during that incubation.
Okay, good. We do have a couple other questions, but some of them are a little bit more complicated. So what we're going to do is we will provide a written response to that when we send out the slides in a week or two. So feel free to continue submitting your questions. We will answer them. But for the webinar today, we will consider it concluded. I'd like to thank Allison and all of the attendees for participating today. And we hope that you've gained a better understanding of some of the challenges of running the 3T3 phototoxicity assay. Judging from the questions, I think a lot of you are dealing with some of the same situations that we are. So I personally feel like this was a very helpful webinar, and we hope that you do too. We'd like to remind you that any questions not answered during the Q&A time will be addressed by Allison, and the answers will be sent to you along with a copy of the slides and a link to access a recording of the webinar. Don't forget to visit our website, www.iivs.org, to find out the date and topic of our next webinar and other news in the field of in vitro toxicology. If you missed us at the recent SOT meeting, IIVS staff will be attending the New York Society for Cosmetic Chemists Suppliers Day, May 12th through 13th, and will be available to speak with you at booth number 1033. We hope to see you at NYSCC or another upcoming meeting. Thank you again for your participation today.